previous presenter did a great job at explaining the company where I work, so I'll thank her for that. Appnexus, my presentation is called Scalable Machine Learning Pipelines for Click Predictions. It's joint work with the data scientist Tien Yu and Jana Volkovic. I'm more of a data science platform engineer, so I'm like in the intersection of the two. Today, what I wanted to cover is basically we have 4 themes for you to take home if you wanted to build something like this or you wanted to apply it to similar kind of environments. And we have one case study that's our production click prediction pipeline. So the 4 themes that I want you to remember at the end of this talk are basically these 4 pillars that we try to agree on as a team. So we have research production parity. We have preventing pipeline jungles. We need experiment versioning for model exploration and fast iteration. And we need to understand clearly what are the trade-offs of model freshness. The case study that I will be presenting is based on the Appnexus platform, which is an internet technology company that powers real-time sale and purchase of digital advertising, so real-time bidding. Our scale is worldwide, 5 continents, which basically encompasses something like 400 billion impressions seen per day. And we transact on that around 10 billion transactions per day as peak. So it's a little, it's like bigger than most, but it's a very challenging problem. And so the numbers, the description that I have for you today is based on our pipeline from 2016 to mid-2017. It changed. It's constantly evolving. So we took a snapshot for you to report back to the community because the literature is very sparse on what are the best practices for this kind of scale and this kind of use cases. So just to give you a brief overview again about how real-time bidding works. When you go to a web page, you have an ad call that goes like, hey, I have this user on my website. It goes to an ad exchange. In this case, we have the Appnexus inBus. And a bid request is sent to a bidder. And the bidder has to make a decision on how much should we bid on this impression. And to do that, it asks for a prediction request. And it gets a prediction response, which has a certain level of probability and like how much should we bid on this impression. That's fed back to the inBus, which runs a second price auction, and then determines if the bid should win or not. And then depending on who won the auction, then the adequate creative is showed to the user on the web page or the app or whichever medium you use for the publisher. So it's a little bit, it's like 20,000 feet sort of view of the world. But if you just want to think about it, from our perspective, it's you have some data that you need to train on, you generate a bunch of models, and then you're able to upload these models through an API, and you execute, by the end of this talk, like hundreds, if not thousands of millions of like auctions will have been running already. And so the opportunity is pretty high. We've seen like the presenter before me said, like a very high interest in digital media, like moving away from TV, and so the IAB, which is like an organism that tries to wrangle all these media companies, estimates $85 billion for 2017. And so to be competitive in this industry, advertisers rely on accurate ad click-through rate prediction. We need to understand how to spend their budget effectively and hit their KPIs. So from our perspective, we need to be able to evaluate the machine learning models efficiently to avoid any timeouts and to optimize for memory efficiency. So the challenge is exactly what we discussed before, is that you have these two forces. At one end, you have you want really low interest rates of technical debt. I remember a talk here that happened from D. Scully about the high interest rates of machine learning. That was really, somebody talks to your problem and you really like it. It's actually a very nice presentation. I welcome you to check it out. But on the other hand, you have how much flexibility should we give to the data scientists so that they don't try out the next big thing without control. So it's like a little bit of a nice trade-off there that needs to be handled. So from our perspective, what like end-to-end, the word end-to-end ML pipelines is so special. We're not talking Kaggle. We're not talking any sort of data-driven competition or ML-driven competition. We're talking production, real money, real transactions. Whole businesses can fail because of overspend or underspend or those kind of problems. So the first lesson that we learned is this idea of research production parity. So the interaction, just to give you an idea, the interaction between data science and engineering, or optimization like we call it, is rely on not only on the classical kind of software engineering things such as packages, but it also relies on data dependencies and data semantics. And so we need to give to the data scientists and to the engineers the right runtimes for their models. We need to take care of the package dependencies, the versions when they evolve, any sort of machine learning package that we use. If a specific threshold changed from version 19 to 21, that could affect business. So we need to be very careful about that. And then the model serving infrastructure is something that never gets taught. I mean, that maybe starts to be taught now, but model serving infrastructure, how do you present these models to the consumers, to serve your model is pretty new, I would say. It's not as explored as it should be. The second lesson that I want to talk is this pipeline jungles. Pipeline jungles basically happen when you have teams that are not integrated, basically data science engineering, where they use different tools. You have all this glue code that happens just to be able to train data into ML models. And mainly it's for transforming data into piping it in and to the model during serving or during training, during testing, validation. And so we came up with this evolution kind of so that you know where you are on this evolutionary scale, where you have at the beginning, when it all started, basically individual custom scripts that people build, and then you move into a shared data preprocessing jobs, so that we actually know what happened to the data before it was fed in the ML pipeline. Then you have a unified data store, where we know which features are in there, and we can reproduce experiments, we can reproduce behavior in production. And then we have a unified ML features store for the models as well, and for the metrics that we're tracking, so that you have a unified place where you have all these elements for you to look at as a data scientist or engineer, so that you can debug problems at 4 a.m. in the morning, and you don't have to start guessing what's happening. The third lesson that I want to share with you is the experiment versioning. So experiment versioning is central to a data scientist's life, where a certain metric is not behaving as expected and we need to improve it. We want to explore this new product. And I invite you all to think about what an experiment encompasses. Where are these boundaries of this experiment? So from our perspective, we consider source code is part of the experiment. So experiment metadata, any sort of config that needs to be handled needs to be part of the experiment. Data dependencies, package dependencies, and runtime. And then what have you. You can add anything, but really deciding with your team about what's the boundaries of an experiment is crucial for your success. Also, what happens is that in a business setting, you want to, I come from an academic setting where I was doing my PhD in computer science, and I was taught that reproducibility is very important. However, in a business setting, you need to understand what's the cost of doing reproducible science, and how far back should we do, should we be able to reproduce. Also, you want to avoid any sort of time travel issues. So that comes for free when you have a unified ML store, where you don't want a situation where the data scientist has access to feature data that happens at serving time, but not at training time. So some data that should not be available at training time is magically available at training time. So defining exactly the data dependencies that you need is very important for you to be able to scale this up. The fourth one is the model freshness trade-offs. So something that we don't think about is this interaction between these four components. You have, on one hand, you have the model update frequency, how frequent should we upload our model, and then then you have what system do you use for job scheduling of these models, and it interacts with the predictive performance. How much log loss did we lose, and then how much it costs to train a specific model family, for example. And so, especially in RTB, the data sources are not fixed. The data sources are constantly streaming, constantly fluctuating depending on seasonality, and so we need to be able to react to it in a fine-tuned manner. So what we came up with is to determine specific job scheduling options and evolution, where you start with, the thing we all love to use is cron, where you play and pray. But then you have better options that you should be exploring. You have things like you have at least something that retries on failures when model training fails, and how many times should it retry. Then you can have a job scheduling mechanism that uses the predictive performance of the model, so that you can determine how frequently should we build the models. And then on top of that, if you use both the predictive performance and the technical cost of training, you can get even better, you can have higher utilization of your systems and lower the costs of producing these models. So the case study that I have for you today is the ML pipeline that we built 2017, is just about click prediction in an RTB setting. So the challenge of this pipeline, it's not a single CSV from the UCI thing. It's 400 billion impressions scenes per day, 10 billion transactions per day at peak. We wanted to focus on how cost effective we can be. And we wanted to enable the team to iterate very quickly on their models without being too locked up into specific frameworks. And then, as I said, we have dynamic data streams. And the key also specifically for this use case is the really tight model serving constraints, similar to edge devices, where you have very tight timeouts and tight resources that you can use. And so we target below 100 millisecond prediction time for a single impression, and so that introduces a bunch of challenges. So we have a paper scheduled for PMLR where we dig in even deeper, but we have like a deep dive in this architecture where we have data gathering, model training and selection, model serving, and model monitoring. I invite you to visit to check out our paper. But I wanted to share with you this spectrum here, where sometimes new users of machine learning pipelines, when they join a real company that's like doing actual model training, you have this spectrum that you need to pick from. And on one hand, you have the full kind of just-in-time feature transformation, where you allow the researchers to experiment with new features by scanning all of the logs every time they want to do anything. And on the other end of the spectrum is when you have a somewhat solidified schema of what are the features that are available in the data warehouse. In our case, we went more with the ML feature data warehouse, and we allow the users to have custom lookbacks. And we can amortize the training, the data pre-processing job for the training data with this data warehouse. It also reduces pipeline jungles, as you can imagine. For model training hyperparameter, like I said, we use like a Spark ML library for that. Its scalability matches our scale. But what's more important for us is our tools that give us sparse models. So, for example, logistic regression with its very good L1 regularization aspect gives us very sparse models that are fast to evaluate at prediction time. Also, some libraries have both like Python and Scala Java libraries, and so it helps with this idea of research prod parity. For hyperparameter search, it can get very expensive, as we all know, and we use like a certain we needed a way to constrain the search space of the hyperparameters. And so we run offline experiments to pre-constrain the experiments. For model serving, like I said, we have bid responses that are very tight, lower than 100 milliseconds. And so here I show the process to actually add a new feature to the serving layer. So it's something that's not covered very well in literature. What should you take into account when you are adding a new feature to your serving layer? Especially when it's managed by a different team, because the team has specific goals in terms of scale. And so you start with selecting a new feature, and then you evaluate its predictive performance first through a data scientist's work. And then you can propose this feature to the model serving team, the bidder team, and then you can evaluate the runtime in a subset of the bidders, and then you can include or reject features. So to give a couple examples, for example, adding a single integer ID as a feature, that's feasible. Adding full text of the ad context, you start seeing a little bit of pushback. And things like adding the full video of the ad context with like, you want to push like a bunch of frames to be, and still have that kind of 100 millisecond timeout is pretty hard. And so the last piece is how we discovered that not everybody cares about all the metrics that are in our pipeline. So we divided the metrics into two channels so that it's less confusing for everybody. We have channel for business metrics, which product managers care about and senior leadership cares about. And those are like click-through rate, delivery rate, spend. But then what's new is that you need to build a whole set of dashboards and alerting systems that just target just the data scientists and the production owners of the software pipelines. And so to look at stuff like prediction bias, what's the log loss on all three types of train test validation data sets, and what are the model parameter ranges. Because model parameter ranges was a surprise for me that like you can actually use those to see the variability in your model across hour by hour training, and then you can tune the frequency of the training. So you can reduce the training frequency and save cost. And at the same time, you end up with similar models. If the models don't change too much across time, then you can use that as a metric to tune your job scheduling. This is very interesting. So if you remember just 4 things from this presentation, I want you to get out with these two. You know, it was to stay with the software engineering for ML kind of ideas. You have, we strive towards research production parity, means like same tools should be used, or similar tools, very close collaboration needs to happen. And then you have preventing pipeline jungles. So if you can go toward a data warehouse where you have enough flexibility for data scientists, I think that's better. But it depends on your data sets, obviously. Experiment versioning. I invite you all to actually just, what is an experiment and what does it, where do you draw that box so that you can determine, you know, this experiment was responsible of this result, and it's a great intellectual kind of exercise. And the 4th one is this model freshness trade-offs, where you can tune your training cost and data processing cost by determining how fresh should the models be before you you decide to update a model. So this, like I said, we have like a fuller kind of description of our pipeline to you know, contribute to the very sparse, like I said, literature about production pipelines. But my collaborators are here to you know, answer any question if you want to contact us. Thank you.
Okay, any questions? Ladies first.
It's not really a question, it's a comment. I think you undersold yourself a bit with the 100 milliseconds, because it's actually network and other things going on in that 100 milliseconds. And I know in our system, we only have 10 milliseconds to respond. Right. So you're probably the same. Yeah, it's
very similar timeouts. Yeah, very similar requirements because you go through a bunch of intermediaries, and so you need to account for that as well. Yeah.
So you discussed about the computational constraints for building features, but for contextualized features, they could be shared for many impressions. So why not have some expensive feature that is computed once from one media web page and then reused many times, and have a pipeline to manage those costly features? Like you could have, for instance, a rendering of an image rendering of the web page and use a neural network that extract an embedding of the visual aspect of the page and reuse that embedding vector for many ad impressions and set up a pipeline to manage this.
To use the content of the, to use even the content of the publisher, right? Yeah, the context. Yeah, that's actually still a challenge, right? Because but even if you embed the image, if you generate an image like autoencoder or like some sort of way to generate like a compressed representation of the image, you still need to be able to refresh it, like every time there is a new content on the web page, and you need to be able to deal with just like a dynamic nature of what publishers put on their web pages. You cannot rely on, I mean, you can, if we're talking like color scheme, like some people fine, but if you're talking about like actual text that's happening on the web page, it gets tricky. But yeah, it's still a moving field, right? We don't have like what I was more like targeting was to reduce pre-processing time, is really to take a look at your pre-processing whenever you have global statistics that you need to build. So if you're normalizing, for example, over hundreds of millions of impressions of rows of your data sets, then do you really need to do that? You know, it comes to a surprise for data scientists, for example, that are not versed in parallel computation into understanding how a distributed median is computed. And so there's like a lot of back and forth in terms of like how much lift do we get from a feature transformation versus should we include it or not? Right? Like, yeah, depending on how the algorithms that are available to us, you know, they have limits, and yeah. Thank you.
Any other questions? Okay.
Hi, Alice Sowerby from .mesh. That was brilliant, really, really interesting. The question that I have is relating to reproducibility. So you mentioned the cost of reproducibility. What, in your opinion, are the factors that contribute to making it a costly thing to do?
Yeah, well, the usual costs in terms of infrastructure costs, in terms of storage, in terms of at which granularity do you need the data to be able to reproduce your experiments. So if your feature transformation is able to compress the data 100 times, then yes, obviously you can store a longer look back of your data set, so you can reproduce what happened last Black Friday versus this Black Friday. But if you want impression by impression, like row by row kind of event by event data sets, then it gets tricky. Then you need to be able. It's not impossible. You just need to filter by who are the most riskiest kind of cases where we have to keep the archived data sets pretty much, and then we need to train the data scientists into what does it mean to be an archive form, because not everything is, I mean, you have S3 fine, but then if you have like HDFS storage, for example, that's a hot, available, great, but then to reduce costs, we need to ship stuff to cold storage, and to bring it back for you to run an experiment on the past year, if it's non-aggregated data, then the cost increases. That's what I meant by how far back and how much it costs.
Right,
yeah.
So it's mainly about the storage and the size of the data sets then?
Yeah, converting, exactly. And like thinking in terms of how you can make your feature transformations, which feature you use impacts how easy it is to reproduce.